Differentiation is one of the major parts of calculus. I'm going to demonstrate some of the basic rules that you need to differentiate by starting with a simple function, y equals 10x squared. First, I'm going to plot a graph of just roughly what the shape of this function looks like on a set of xy axes, and you'll see soon how this comes into play with differentiation. So a y equals 10x squared graph sort of has a curve sort of like this, which I've just labelled. Now, y equals 10x squared allows you to plot the graph. However, there are a lot of other things about a line you sometimes want to know. For instance, the slope of the line is often interesting. So where I'm putting these crosses, I'm also drawing a line which is showing the slope of the function at those points. And this is one of the many things you can use derivatives for, or differentiation. So first of all, we need to know one of the basic rules of differentiation, which is if we have a general function y equals a, some constant a, times x to the power b, then the derivative of this function, which I'm going to use a y dash to indicate that I'm calculating the derivative, is you put the b out in front, multiply it by the a, multiply that by the x, and then reduce the power of the x by 1. So for our particular function, a equals 10, because that's the thing in front of the x, and b equals 2, because that's the power x is raised to. So what we're going to do is use this rule to work out what the derivative of y is in this case. So y dot equals, or y dash, equals b, which is 2, times a, which is 10, times x, and we reduce our power of x by 1. So it's going to equal 20x to the power 1. Now anything to the power 1 is just the same thing again, so 20x is our answer. Now, say we wanted to find the slope of that graph we've just plotted at a certain point, say at x equals 4. Well, we can use this derivative we've just worked out and sub in 4 instead of x. So, the derivative of our function at 4, which is what I've done with the brackets there, is 20 times x to the power 1, which equals 20 times our value of x. Now I'm just rubbing out the power of 1 because we don't really need to indicate it. 20 times 4. And 20 times 4 is 80. So the slope of our graph is going to be 80 at x equals 4. So that's one of the many uses you can use derivatives for. So that's not the only rule of differentiation there is, but I'm going to practice a little bit more with it first to get comfortable. So here's another function, y equals negative 3 x to the power negative 4. Now, to find the derivative of this, we take the negative 4 and put it out the front, multiply it by the negative 3, multiply that by the x, and we reduce our power of x by 1. So negative 4 minus 1 will be the new power. So y dash equals negative 4 times negative 3, which is 12, x, and negative 4 minus 1 is negative 5, so that's our answer for the derivative, 12x to the power negative 5. So let's keep going, and here's another very simple function, y equals 10. Now notice first of all that there doesn't seem to be any x's on the right hand side of this equation. What we can do, however, is by remembering that anything to the power 0 is 1, we can write an x to the power 0 on that side, because since x to the power 0 equals 1, y equals 10 times x to the power 0 is just going to equal 10. So now we can use that same derivative rule, which we've used before. So y dash is going to equal, well, we put the 0 out in front, multiply that by the 10, multiply that by the x, and we reduce the power of x by 1. Now this is pretty simple. When you multiply anything by 0, the answer is 0. So what we've just shown is that when you find the derivative of a constant, which doesn't have any x's in it or anything, the answer is 0. What about when you've got more than one term in your equation? So here we've got 2x squared plus 3x plus 4. Now 3x is like 3x to the power 1, so I'm just putting that in there to make it a bit easier. So when we derive this, the 2 goes in front of the other 2, the power of 2 reduces by 1, the 1 goes in front of the 3, and the power of x reduces by 1, and the 4 is a constant, so it just is 0. So if we multiply this out, we've got 4x to the power 1, which is just x, plus 3, because we've got 3 times x to the power 0, which is just 3 times 1, which is 3. What about when we've got sine and coses in our equations? Well, if we have a function y equals sine x, the derivative of y with respect to x, which we can show by a y dash, is just cos x. So the type of function just swaps over. However, when we have a function y equals cos of x, our derivative of y is actually negative sine x. So when you derive sine x, it becomes cos x. When you derive cos x, it actually changes sign and function and becomes negative sine x. There's a couple more rules you need to know. If we have a function y equals e to the power x, e is a special constant which comes in useful with natural logarithms and a lot of other stuff, then the derivative of it is exactly the same thing. The derivative is e to the x. If we have y equals the natural logarithm of x, which is ln of x, then the derivative of this is 1 on x, but only for values of x which are larger than 0. Because think about it, if you put 0 into this derivative, you'd get 1 on x, 1 on 0. 1 on 0 is undefined. So it's only valid for values of x larger than 0. So what I'm doing here is going to show some of the different ways you can talk about derivatives. So one way you can write the function is y equals 10x squared. Another way you can write a function is f of x, or the function with respect to x, is 10x squared. So the way we've been writing derivatives so far is just using a y dash. However, there's a couple of other ways you can write it. You can use a d on dx sort of symbol, like I'm writing here, and after the top d you put the function which you're differentiating. So in this case the function is 10x squared, that's what we're differentiating, and you write the actual derivative on the right hand side. So that's another way of writing it. So there I've got the mouse over the 10x squared, and on the bottom you've got the dx. Now, say we wanted to write the derivative from an f of x perspective, well, you just need to add a dash. So like we went from a y to a y dash, we go from an f of x to an f dash x.